Nasser, remind me if the time is over, يعني. So,
Inshallah.
okay, so today, inshallah, we'll see some of the multi-objective optimization techniques which handles the problem as a true multi-objective optimization problem. Last class we discussed some of the conventional technique or traditional techniques for multi-objective optimization, where the problem is converted to single objective with some weights and so on. We discussed the three methods: weighted sum, goal programming, and the epsilon constraint method. We highlighted some of the drawbacks of such methods in terms of it gives you only one solution. It needs to be run several times in order to generate the Pareto optimal set. If the problem is non-convex, so the trade-off or the Pareto front will not be complete. And several drawbacks as discussed earlier. In general, for multi-objective optimization, we need clustering algorithm, which is discussed last time, and also the best compromise solution. So after getting the Pareto optimal set, you need to introduce to the decision maker the best solution or best compromise solution among all the objectives. So how to extract this best compromise solution? We have several methods. Here we discuss one method, which is straightforward. Upon having the Pareto set of non-dominated solution, it is required to present one solution to the decision maker as the best compromise one. Due to imprecise nature of the decision maker's judgment, the ith objective function, Fi, is represented by a membership function mu I as follows. Actually, there is an important point, an important difference between the multi-objective optimization techniques that we will discuss now and the traditional methods is that after getting the optimal set, you present it to decision maker to judge or to extract whatever solution is preferred. But for traditional methods, the decision maker judgment is done before optimization. And when you set W1 and W2 and W3 and so on, this is a decision maker judgment. So the decision maker judgment is done before the optimization. But for the multi-objective, you do optimization, and at the end, the decision maker can judge since he has several solutions or the Pareto optimal set. So each solution can be defined as such. You can give a solution like a weight or a membership function value, or طبعا of course if we covered the fuzzy logic, then membership function is the concept of it would be very clear. But anyway, you can assume in any solution will be normalized. Let us say normalized between 0 and 1. You give it a weight for each solution between 0 and 1. For each objective function, this is the actual objective of the, you have several solutions. This is the Pareto set. So for each solution, you have, for example, for F1 and F2. So this is F1, and this is F2, and this is F1. So this is the objective. So you can have the weight in terms of the first objective. So this is the actual value of the first objective, and this is the maximum value of the first objective. Maximum value is here. This is the maximum value, and this is the minimum value of F1. So you have, since you have the Pareto solutions, you can identify what is the maximum value, what is the minimum value for each objective. So this is the maximum for the objective 1, and this is the minimum for objective 1. This is the maximum for objective 2, and this is the minimum for objective 2. So you can have for all objectives the minimum and the maximum. And you can give this membership function value here as mu I equal to 1 if it is less than minimum, 0 if it is greater than maximum, and any value in between is defined as such. Maximum minus the actual value over maximum minus minimum. So this value will be between 0 and 1. So this value will be between 0 and 1. So this is for each objective of a solution. Yani, for example, this solution, for example, will be given mu1 equal to, for example, this is near to the maximum, so will be very, very low, 0.2 مثلا. And mu2 you can calculate it. This is here you can calculate it 0.7, 0.8, whatever, 0.7 مثلا, for example. So this solution also will have a membership function 1 equal to, what do you think? This is better regarding F1 or worse? So this solution for F1 minimization. What do you think? Mu1 would be?
Better.
For F1, if we need to minimize the F1, but this is the best solution. This is the best for F1, right? This is the best of F1, and this is the best of F2, and this is the best of F2. This is the minimum value of F2, and this is the best of F1. Am I right?
Yes.
So if you are far from the best solution, that means you if you go further from the best solution, so you expect the mu1 will be less or higher. Higher. So this could be 0.4, and the mu2 here could be 0.5, for example. Okay. So this is and so on. You can, for each solution, you can get mu1 and the mu2, according to this. You know the maximum values of each objective and the actual value of the objective, so you can find mu1, mu2 for each solution in the Pareto set. This is just a representation of the the membership function. So this is the F minimum, value of is 1. F maximum, the value is 0. In between, you can have any value here. In between, or any value between minimum and maximum, you can have it. Okay, so F minimum, F maximum, maximum value of the ith objective among all non-dominated solutions, and the membership function value ranges between 0 and 1. For each non-dominated solution K, the normalized membership function mu K is calculated as such. Now you calculate mu1 and mu2 for each solution. So you can calculate now the overall membership function mu K equal to the summation of mu mu1, mu2 over the summation of all the objectives and also summation for all solutions in the Pareto set. Okay, so summation of all in the Pareto set, all solutions in the Pareto set, where M here is the number of non-dominated solutions. So the best compromise solution is that having the maximum value of mu k. So the solution that gives you the maximum of mu k, this one is selected as the best compromise solution. Yes, Al-Fawzan, you have a question.
Yes, question, Doctor, about the slide.
How to?
The previous slide, actually, there is a membership function. We have the term for the fi max minus fi divided by the difference between maximum and minimum.
Okay.
So I could see this is from the graph, shouldn't be multiplied by a term here because it's like a decreasing. It's like a slope actually decreasing. Shouldn't be multiplied by a function here.
No, if you want to calculate this, okay.
Yeah.
So this is the point. Now, what is the slope now? The slope of this line is 1 over the difference.
Yes.
And this point, if you want to have it, so this value, okay, this value is what? This value is the actual function.
Yes.
And this is the actual value of the function.
Yes.
No, this is not the actual value of the function, assuming that this is the membership value, and this is not any okay. So let us take let us get any point in this. Okay, this value is let us say we have here fi. This is the value of fi between f minimum and f maximum, or we call it fi here, right?
Yes.
This is fi, and this is mu. This value is mu I.
Yeah.
So this point is represented by this point. You can write it as an equation or as a point with the coordinate of fi and mu I.
Yeah.
So you can say here this point, you can write it also as f max
0
and 0.
Yeah.
And this point f minimum and 1.
Yeah.
This point. So you can do a very simple calculation here, and you can write here this, which is f max minus fi, this over the total, and you can write here f max minus fi over f max minus f minimum, this over this,
yes,
equal to this over this. Okay,
yes.
This one is mu I, sorry, this one is mu I over A over 1.
Over 1.
Mu over I over 1. So this is the function. So this is exactly what we have here.
Yeah, I'm saying actually, since I thought that it should be like, because it's like a decreasing function, so I thought that there should be like a term that should be multiplied by this, by the difference that we have here, the slope equation.
Actually, we are not decreasing. We are not do some يعني recursive formula.
Yeah.
And we are calculating a certain value.
Yeah.
Okay.
Yes.
Okay.
Clear.
Okay. So you have the this, and you can calculate for each solution. For each solution in the optimal set, the Pareto optimal set, you can summation of all mu k mu1 and mu2 for all objectives over summation for all objectives for all members in the Pareto set. And this is the solution, or this is the summation of all objectives, and this is the summation of all solutions. And you are weighting this solution, a specific solution where you have here a sum of objectives of value or of solution K. This is the objectives, summation of the objectives of a certain solution over the summation of the O. This summation of the all is constant for all solutions. And if you add all mu's for all solutions, but this will be constant. And you have here a summation of mu1 and mu2 for solution 1 over a constant here. Solution 2 over a constant, solution 3 over a constant. So the maximum value gives you the best compromise solution. Is it clear, Shabab? Fawzan, do you still have a question? Do you still have a question, Fawzan?
لا يا دكتور لا.
Okay. Any question? Abaziz.
Yes, Doctor. The best compromise solution doesn't necessarily mean that the solution is closest to for example, the point 0, like in the graph f1, fx, or it's not related to.
F0 mean for the previous graph, this one? Or
Yes.
Next one? Actually, graphically, you can say, let us, so this is M, the number of solutions in the Pareto set. Actually, you can say the best compromise solution that the one nearest to the origin, the minimum distance to the origin. So this is the optimum solution. These are the optimum solution. These are the Pareto set. This is the Pareto set. The best compromise solution is the one which is the nearest to the origin. So this one is the best compromise solution. If you check this formula and that, if you normalize all the objectives in order to calculate the distance here, you need to normalize the objectives, and you know how to normalize the objective. You can have the objective normalized if normalized equal to fi minus fi minimum over fi max minus fi minimum. So you convert each solution to between each objective to between 0 and 1, then you can get the distance to the origin, which is f1 normalized square plus f2 normalized square. So this is the distance to the origin. So you can get also the best compromise solution using this simple concept. Is it clear?
Yes, thank you.
Let us move to now the multi-objective optimization technique. Actually, there are several methods for the multi-objective evolutionary techniques. One of them is non-dominated sorting genetic algorithm, NSGA. NSGA have another version, or advanced version, which is NSGA2. We have also 3. We have NSGA3 as well. These are some of improvement on the initial version of NSGA. Improvement in order to reduce the complexity, in order to reduce the computational time, in order to cover some of the limitations in the original one. This is one type of, or one method of the evolutionary algorithms, multi-objective evolutionary algorithms. There are other methods. One method, but then actually I was included all these methods in this part, but due to the expected, squeezing the term, I removed the other one. We will discuss only NSGA and the NSGA2, but we have NVGA, non-dominated Pareto genetic algorithm. We have also SPEA, which is also widely used, strength Pareto evolutionary algorithm, and we have also SPEA2. So we have another version of SPEA. We have different methods of multi-objective optimization. But let us concentrate on NSGA and NSGA2. If you need to know more, then we can do it out of the class time. Then time is very short, and we expect also to start the exams earlier, and we are waiting for any information from the university in this regard. So NSGA is developed in maybe in 1990, 95, 94. A ranking selection method is used to emphasize the current non-dominated solution. I would like to remind you with the distinct properties of the multi-objective optimization. We need, in the selection process of genetic algorithm, we need to be more biased to non-dominated solutions. We cannot compare all the objectives, but we can identify the non-dominated solutions, and we can give priority for the non-dominated solutions to survive for next generations. So in this case, we need to have a fitness function which reflect the dominance of the solution. So, and the selection will be based on this dummy fitness. This dummy fitness has nothing to do with the original objective functions, but it reflects the dominance of the solution. So this method, NSGA, starts with the ranking. You rank all the solutions in the population. For example, if you have these solutions, I need to do it in a more professional way, and we need to okay. So if these are the solutions in a certain generation, population size here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 solutions for each generation. Assume that this is a generation, and these are the solutions. Can you rank them in different fronts or different ranks according to the dominance. Where is the dominant solution? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, whatever. I thought no. Okay. So can you identify the non-dominated solution in this population? What are these solutions? Nasser Hakami.
1,
1,
1, 2,
1, 2, 3.
and 4.
Huh?
4 also.
4.
Yes.
خلينا نحط 4 هنا.
Same
الفور ها؟ الفور لا 4 is little bit up on a 3. Okay. So assume that no 4 is not 4 is covered by 3.
Okay.
Yeah, let us shift it يعني little bit higher. This is why. Okay. So this is the first front. So take these solutions out of the population. خلاص, this is the first front, so let us keep them aside. This is front number 1. This is front 1. Or rank 1. Okay, excluding those solutions, can you get the first or the non-dominated solution of the remaining?
Yes.
What are those?
6, 5, and then 4.
So this is rank 2. And exclude this rank, and the remaining also you can do the same. So you have here a third rank or third front, and this is the fourth front. This is front 4, and this is 3, and this is rank 2 or front 2. So this is the ranking process. So this ranking process reflects the dominance. So whatever in rank 1 or in front 1, the solutions that represent front 1 is better than front 2 is better than front 3, and so on. So you can say, okay, in order to, to identify the solutions that should be selected for mating, we can say, okay, the first front will be given like fitness, very high fitness, like 10 مثلا. So the fitness of this solution is 10, the fitness of this solution is 10, the fitness of this solution is 10. And let us subtract some value, 1, 2, 3, epsilon, whatever, 2 for the rank 2. Rank 2, you can have it 9 مثلا. All the solutions here are given a dummy fitness equal to 9. All the solutions here are given a dummy fitness equal to 10. And then this 8 and this 7. And you have a dummy fitness which reflects the dominance of the solution. So when you want to select 2 solutions randomly, and you want to select the better one. So if you select one solution from this front and one solution from this front, you look at the dummy fitness. This is 10 and this is 8. So I will select a 10, which is better one. And if you select between مثلا 8 and 10, which one you select? Which one is better? So you select 8 is better, and the fitness here is higher than this one. So you replace now in the selection process you replace the actual objectives by a dummy fitness that reflects the dominance. So we can do this. This is very simple. When you select any two solutions randomly for the selection process, you can look at the dummy fitness and select the better. طبعا of course you can say no, okay, if I take x1 and x2, if I have 1 and 2, what should I do? Of course, you can, for the time being, you can say I will select any one of them. They are non-dominated solutions with respect to each other, so I will select any one of them. This is okay for the time being, but later we will see how to modify this dummy fitness to also take into consideration the first important point for the optimization, multi-objective optimization, which is we need the solutions to be well distributed. Now, as we mentioned earlier, we have two objectives for multi-objective optimization. We need to find the Pareto optimal set, and also we need to find a well-distributed set. Okay, so we have to take this into consideration. We will see this. We will see how to incorporate this concept here and modifying this dummy fitness. But this is the first step, dummy fitness according to the ranking, and then we will see later what should we do. Fawzan, do you have a question, Fawzan?
Yes, Doctor. How did you assign this fitness?
I didn't hear you well, Fawzan.
Dummy fitness. How did you assign them?
Yeah, assign them. The concept is you can say no. I will have this equal to 10, 100, 1,000, whatever. 1, حتى 0, and this becomes -1. This is -2, -3. And any dummy, it's called a dummy fitness. And assume that this is 10, for example, and I need to differentiate between this one and this one. I subtract from the 10 1 مثلا, or 2 or 3 or whatever. This is dummy. Okay, حتى لو ده هنا 0 -2 -3, I need a dummy fitness in order to say when I select two solutions randomly, I look at their dummy fitness, and I can, from this fitness, I can identify which one is better. This is the whole idea. So this is dummy fitness.
Like a map.
Huh?
We map them to any number.
Yes. You can start with 0 and -1, -2. You can do the opposite, by the way, and you can say no, this one will be the minimum value. I start with 0, مثلا. And then I increase. Opposite. This is 0, 1, 2, 3. Or I can say in the front 1, I will give it 1. Front 2, I will give it 2. Front 3, 3, 4, 4, and so on. And in this case, when I select, of course, I will look for the minimum value, right? Minimum value here is represent the better solution. Am I right or not?
Yes.
And you can reverse the concept, but the idea is when you rank, you assign a dummy fitness, and based on this, you can do the selection. This is the whole idea.
Okay.
Muhammad Sabah.
Yes, Doctor.
Yes, please.
My question is, how did we generate this Pareto front through the classical method, and how did we generate the whole solution randomly?
لا تاني كده one by one.
First question, how did we generate this Pareto front?
This Pareto front?
Yes, is it through the classical weight method?
لا أنا I mentioned إنه this is generation. Now we are moving to the multi-objective evolutionary algorithm, NSGA, is the non-dominated sorting, ranking,
Yes.
genetic algorithm. So we are talking now about genetic algorithm. So we have generation, and then we need to selection, and we need to go the generation 2 and the crossover mutation, and then we go to generation 3 and so on. This is genetic algorithm.
Yeah, so we are talking about multi-objective genetic algorithm.
Yes.
And this is how we generate this, but is it also through the weighted sum?
Not how to generate. And we are not generating.
No, I'm asking how did we generate the solutions now? Is it we start randomly, but still we have two objectives?
Okay. In genetic algorithm, how to start?
We start generating random solution, and then we do mutation, selection, mutation, and
Okay. Exactly.
but
yes, you are right.
yeah, but the question is, I'm trying to link it with the multi-objective.
Okay. Right.
So I need to modify the genetic algorithm to handle multi-objective.
Okay. Right. Nice. Okay. So assume that Muhammad, assume that this is the initial population, that you create them randomly.
Okay.
And these are created randomly now. This is
Yes.
the initial population. The addition here over the genetic algorithm is that each solution, of course, for each solution of those, you can calculate J1
And
you have
J2.
J1 and J2. For X2, you have also J1 and J2, right?
Yes.
Based on J1 and J2, J1 and J2, and so on, based on these objectives, you can identify whether this is a non-dominated solution or dominated solution.
Yes.
Am I right?
Yes. Yes.
So this is the ranking. And how to rank this? How to rank these solutions here? And how can we identify the non-dominated solution? In genetic algorithm, you are not displaying the objectives of the solutions, and you can easily identify by inspection. Am I right?
Yes.
And even this is only can be carried out for two objectives. But if you have
Yes.
3 objectives or 4 objectives or 5 objectives, you cannot do this. You cannot visualize the
Yeah.
solutions, right?
Correct.
So how to identify these non-dominated solutions? This is based on the values of J1, J2 for each of these. The dominance conditions.
Yeah. The distance.
Okay. What?
Distance.
This
Right.
no, the dominance. Dominance
Yeah.
condition. And no, Ji is less or equal.
Oh yeah. The condition should be less than, and at least one of them is less.
Exactly. Yes. For all, and there exist
Yeah. Okay.
at least one.
Clear, doctor. Thank you.
Okay. Based on those, you can identify which one is the non-dominated solution. So this is the first front, and you compare all those, the remaining, and you identify the non-dominated solution. So this is the second front, third front, and so on.
Yeah, and then repeat the same in the next generation after selection and mutation.
Exactly. Yes. Exactly.
Thank you. Very clear, doctor.
Okay. So this is the ranking selection method is used to emphasize current non-dominated solutions. And in order to keep the diversity of the solutions, and you end up with the well-distributed Pareto front, you need to implement this niching concept here to this. Niche concept is very simple, but it tells you, if you have another solution here which is very close to solution 2. At the beginning, you assume all the dummy fitness of these solutions are 10. And then this is 10 and this is 10 and all these are 10. Then you can do the following. You can say, okay, I will look at the crowded area here. and I will degrade the fitness value according to this crowdness that we have here. And we have here 2 and this solution number 13 مثلا. 2 and 13 are very close to each other. So I will degrade their fitness here. It is not 10 no more, it will be less. It will be, for example, 9 and 9. So when I compare between this and this, when it comes to the selection and I will find out, these solutions are selected randomly, which one is better, I will select this one. Then the fitness here will be degraded. Why degraded? This area is crowded. We have so many solutions. In order to keep the diversity, we will take this solution. So this is the niching method is used to maintain the diversity in the population. Of course, you can say here, when we degrade this, for example, if its fitness function becomes, for example, 9. Okay, so this solution is comparable with this solution? No, actually, when we assign the dummy fitness, we assign the dummy fitness for the whole solutions in the front. And then we do niching here in order to degrade the crowded solutions or in the crowded area. And the minimum that we have here 9, we have here 8, مثلا, for example. The minimum here is 8. We subtract from 8 an epsilon, and we start with the second front. So if this is 8, the minimum in the first front is 8. So we'll start this by 7, which is minimum than the minimum here. And these solutions are the superior solution in the population. Did you get the point? Do you have any question? Okay, so we do niching, and we will see how to do niching now in order to maintain the diversity in the population. The algorithm includes 2 main steps: the ranking and niching. Fitness assignment by ranking, and the other step, which is doing niching and fitness sharing. We do what's called the fitness sharing. We assign 10 at the beginning. This is the first step. We identify the non-dominated solution, and then we assign dummy fitness for all solutions. And then we do niching or fitness sharing, and then we degrade the fitness if there are so many solutions around that solution. So, and we take the minimum, and then we go to this one. We subtract epsilon, and then we go to the second, the front, and so on. So this is the fitness assignment and the fitness sharing. So let us see the first step, which is the fitness assignment. So many. Okay, Hisham Muhammad, do you have a question, Hisham?
Yes, Doctor. I would like to ask about if the solution in the border of the ranking.
Solution in the border, we mean 3 مثلا?
لا, for example, in the border. on the border of the between the line between 2 ranking, for example.
لا، ما هو مش هيبقى between 2 ranking. هو يا اما هنا يا اما هنا. Either in this front or in this front. يعني you cannot find a solution which belongs to both. Did you get the point?
Yes.
يعني none of the solutions will be belong to 2 ranks. And you cannot find it. If you have any, you can imagine a solution that is in between. cannot find. And definitely, if it is here, it will be either covered by this or covers others. Okay, so you cannot find one of the solutions is in between. No? And this is should be distinct. Yeah.
So, okay, actually, Doctor, I didn't get the idea about the fitness sharing.
What is the idea?
What is the idea of the fitness sharing?
The fitness sharing is to degrade the fitness assigned here, degrade it according to the the crowdness in the area here. If you have an area which the solutions are very crowded here, you have so many solutions here. Okay, and you assign 9 as a dummy fitness for all the solution in this front. You come to the niching here method and say, no, okay, this solution is almost alone. So I will give it like a certain sharing or certain value. For these solutions, where you have here so many solutions here in this area, so these solutions, we will degrade their fitness. And instead of 9, it will be less than 9. So when you select 2 solutions and these solutions are within the same front, you will prefer this one over this one. You will prefer this one over this any one of the solutions here. And the fitness here is 9. The fitness here will be less than 9. And we have so many solutions in this area. Did you get the point? So you have fitness assignment at the beginning according to the dominance. Within each front, you will go and see what are the the area that contains so many solutions, and you adjust the fitness assigned here. Okay, you adjust it in this step, the fitness sharing. Is it clear, Sham?
Yeah, now it's clear. Thank you, Doctor.
Okay, Nasser Hakami.
Doctor.
Yes, please go on.
Yeah, for me, I think it, as I understand, is if it is 9, it's mean it's good for one objective, but for example x6, it is good for one objective, but the other is not good. So the one in the middle should be better. So why we should rank it less?
لا in the middle is not better. يعني what is the definition of better here يعني?
Better is mean compromise between 2 solutions. I'm getting a best of F1 and the best of F2, not just going to the F1 only.
We are not searching for the best compromise. We are not searching for the best compromise. Best compromise solution, this is at the end. When we finish optimization, when we have the Pareto optimal set, if you want to identify a certain solution as a best compromise, you can do this. But during the optimization, all the solutions, we are not searching for the best compromise. We are searching for well-distributed Pareto set, diversity and optimality, or the quality of the solutions.
So until now, it is only a distribution and arrangement. We did not reach that we can evaluate a set better than another set.
Again.
For example, now we are in, I know by default that the set, the front one is better than the front two, but within the one, why am I making that one is 9? Because it's just only crowded, or because its locations more to the right?
No. It's crowded.
That's the only reason.
Yes, this is the reason. The crowdedness.
Maybe so if it is crowded in the top, that also means you should give it 9.
You are right.
It's not about that because that in the extreme, because I thought that the x1 and the extreme, because they are the extreme point. Okay.
For example, you will grade the fitness of these solutions in a very crowded area. You will degrade the fitness of those solutions in a crowdedness area. Okay? Is it clear? So it is not related to whether it is in the middle or in the extreme, but the idea here in the area is crowded. When you have so many solutions around that solution, these solutions will be degraded. Fitness of these solutions will be degraded. Okay?
Okay, Doctor, clear. Thank you.
So, okay. So these are the two steps that we have here in the non-dominated sorting genetic algorithm: the fitness assignment and the fitness sharing. Okay, so let us see the fitness assignment. The basic idea of this approach, as we discussed, now we already explained all these steps. The basic idea of this approach is to find the set of solutions in the population that are non-dominated by the rest of the population. You have the non-dominated solution. Front number one, first front. Consider a set of n population members, each having an objective value. The following procedure is used to find the non-dominated set of solution. Initiate the individual counter, okay, for all solutions xi, compare xi and xj. This is the dominance. You compare for dominance, okay, for domination. You apply here the the conditions for the domination, and then if for any j xi is dominated, you mark it as dominated. And whenever you have a solution, you start from solution number one. And you have for loop from I equal to 1 to n population size in the book. Okay. And then you start another for loop from j equal to from 1 to n bob also. But if I equal to j, this is j. If I equal to j, skip. خلاص, this solution is already considered here. So this is x, or also for this is the condition here. For all solutions j not equal to I, you compare. Okay, this is you can go to another j. You can skip this j and go for another j. Otherwise, you can compare this solution and this solution. Which one is dominant? Which one is non-dominant? If a solution j is dominated by I, you mark it as dominant. خلاص, you exclude it from the time being. خلاص, this j is dominated by I, so you mark it as dominated and you exclude it. And then you go to another j. Dominated also, you exclude it. You mark it as dominated and so on. You go for all the solutions. The solution that is not marked as dominated, this is the non-dominated solution. So these are identified as the non-dominated solution. So for any j, xi is dominated by xj, mark xi as dominated, and go for another solution, and so on. If all individuals, all solutions in the population are considered, go to step 5. Else, go back and to check another solution, and so on. You increase I by Rasul. This for loop. You continue until you finish. All the solutions that are not market dominated are the non-dominated solutions. And this is, if it is done for the first time, but this gives you the first front. Okay. If this is the first front, exclude all these solutions from the generation or from the population, and then you repeat these steps again. And you you come up with the second front. You exclude all these solutions, first and second fronts, and you do this again. So you have the non-dominated solution of the third front, and so on. So these solutions represent the first front, and they eliminated. This process continues until the population is properly ranked. Front 1, front 2, front 3, front 4, and so on. Is it clear? Computational flow is clear? Okay. So this is the case. You have the population, and this is the first front. Definitely, when you exclude these solutions from the population and you do it again, you need to identify the non-dominated solution. So most likely this will be the second front, and this will be the third front. Okay, so you rank them as such: first front, second front, third front, until you finish all the solutions here in the population. So this is the how to identify first front, second, third front, rank 1, rank 2, rank 3, and so on. You rank all the population: first, third front, fourth, fifth, and so on. Now, fitness sharing. The basic idea behind sharing is the more individuals are located in the neighborhood of a certain individual, the more its fitness value is degraded. The more individuals near to a certain individual, the more its fitness is degraded. Neighborhood. How to define the neighborhood? How to define the neighborhood? These solutions, okay, these are some of the front, a certain front, okay? So how to define the neighborhood? Here you have to, yes, Nasser?
By the distance.
Yes, you can write, what we call sigma share. Sigma share is a distance. You can say, for example, if any solution within like this neighborhood with the circle here, with this radius, 0.1 مثلا, this is a distance. So within any solution within this circle, this becomes in the neighborhood. Outside يبقى خلاص يبقى this one مثلا, for example, none in the neighborhood. Maybe this one, if you have this sigma share, if you define it as 0.1 or 0.2 or whatever, this is a key parameter, and this is one of the drawback of NSGA, which is overcome in the NSGA2. We don't need to then this is subjective. And 0.1 maybe 0.1 is very high, we don't know, or 0.01 is very low, we don't know. And this is subjective. But anyway, if you set here a distance, and any solution within this distance, you can say that this is in the neighborhood. Otherwise, it is in the out of the neighborhood of this. So if you have so many solutions in the neighborhood, so you degrade the fitness of that individual. Nasser, you have a question?
Yes, I have a question. If we have the best of F1 and F2, and then I take the distance, for example, I divide it by n equal 10, and then this will be the sigma for me. So the distance will be 1 over the highest distance between the F1 and F2 best solutions.
You are right. This is one way to set it. You can see the whole distance between minimum and maximum. But when we say distance, okay, in this case, we need to normalize the objectives. We need to normalize the objectives.
Yes, sure.
You have J1 and J2. Then what is the distance between these ones? It is J1. If this is, for example, solution number I, and this solution number J. So F1I minus F1J square plus F2I, second objective for this solution, minus F2J square. So if these are normalized, that's fine. But if it is not normalized, in this case, this is not right. And maybe the difference here may be in hundreds. The difference here is in, very small value. You can say in order of 0.1. So you cannot add 100 to 0.1 here and you get the distance. But you have to normalize, and you know how to normalize. So this is between 0 and 1, and this is also between 0 and 1. So you need to normalize, and you get the whole distance, you are right. And then you can say no sigma share equal to the distance ij over 10, مثلا. Similar to what we have done in which technique? This neighborhood, which technique we discussed here, and we defined the neighborhood.
Finishing.
I think clustering.
In clustering, and also in
Particle swarm.
particle swarm, and
We have
also
the N.
in simulated annealing. In simulated annealing. Okay, we define the move, or we define the neighborhood, and you create a trial solution within the neighborhood of the current solution. Okay, so yes, you define a neighborhood by a radius, and then this radius can be set as the distance over 10. So this is sometimes you divide by 20, sometimes you divide, and so on. So this is a subjective value. The neighborhood is defined in terms of a distance d specified by the niche radius sigma share. Given a set of nk solutions in the k front, in front k you have a number of solutions equal to n, each having a dummy fitness value fk, اللي هي 10 وال9 والكلام ده. So we have a dummy fitness is assigned for the front. Now we will go to the solutions in the front, and we will see for each one of those solutions, we will see the neighborhood of each one, and we calculate the distance among all these solutions, and we see which one is in the neighborhood of each other, and then we degrade its fitness. So you compute and normalize the Euclidean distance measure with another solution J in the case non-dominated front. You measure the distance between all these solutions. You measure the distances between all these solutions. Euclidean distance. As we just pointed out, square root of J minus J, or F minus F square plus F minus F square. But these are normalized, should be normalized. And we discussed already before how to normalize that. Okay, so you can calculate the distance. This is the normalized distance between f max minus minimum divided by max minus minimum for all the objectives plus again and so on. Where an objective, the number of objective parameters, f k max, minimum distance, okay, with f k. Okay, so we calculate the distances between or among all these solutions. This distance dij is compared with the pre-specified parameter sigma j. If dij is less than sigma j, we have solutions in the neighborhood or what? Or not? If dij,
it is in the neighborhood.
yes, if dij is less than sigma share, we have these two solutions in the neighborhood of each other. So we will degrade their fitness. And instead of I, we will divide it, or we will, reduce it. Okay, so let us continue. We will define for each solution, we will define what we call sharing. Sharing depends on dij. If dij less than sigma share, we have sharing equal to 1 minus dij over sigma share square. Okay? Zero otherwise. If it is outside the sharing, the sharing equal to 0. If it is outside sigma share, if dij is greater than sigma share, outside the neighborhood, the given here sharing equal to 0. Okay? طيب. This is done for all the solutions. What is the minimum value of the sharing of dij? What is the minimum value?
Zero.
If the solution is outside, if I equal to j, if we have the same solution, so this distance becomes 0, and the sharing for the solution becomes 1, and this is the minimum. This is the minimum sharing for each solution. It is 1. In the neighborhood, if we have another solution in the neighborhood, we have another value here. And this value, of course, this is, we have some kind of summation. Let us see the next equation. This you have, for each solution, you have the summation of all sharing, and then you calculate the sharing of the solution. Increment j, and you go for another solution in the neighborhood, in the front, until you end up with you cover all the solutions in the front. And then you calculate sharing of the front m of the solution mi equal to the summation of the sharing with respect to all the solutions in the front. Okay? So I don't know whether you are following me or you have any question. And you start here for each solution in the front. As we mentioned, you calculate all the distances here, and you know that this compute a normalized Euclidean distance for a solution J. So you vary here. This is Ij, distance between any two solution I and J is distance as such. And based on this distance, you calculate the sharing here. If this is 0, then becomes 1. If this is any value below, sigma share, you can calculate this, and otherwise it is 0. And for each solution, now that this is, assume that, for example, in we have a solution I. This is a solution I. This is a solution 1. Solution 1. You have distances. This is 1, and this is 2. This is solution 2. This is solution 3, 4, 5, 6, 7, and so on. You have sigma share. You compare the distances here. These are the distances. So you have 1, and the distance between 3 and 1 is below the sigma share. So you calculate this value. D1, D13 now. D13 is lower than, so share of D13 equal to a certain value comes here. Okay? D11 مثلا خلينا نقول D11 D11 distance 11 D11 equal to 1. D12 equal to 0. Maybe 2 is outside the sharing, outside the neighborhood. So D12 is 0. D13 is within the neighborhood. You calculate it. If it is مثلا 0.1 of those or 0.7, the ratio here 0.7 square يبقى 0.49, 1 minus يبقى 0.51. D140 مثلا. D15 in the neighborhood. So D15 will equal to D15. Distance here is, for example, 0.5 of this. Square يبقى 0.25, 1 minus يبقى 0.75. And so on. Summation, this is M1. You calculate it. This is M1. And you repeat this for solution number 2, solution number 3, and so on. طبعا احنا when you calculate distance, you have matrix, distance matrix, 1, 2, 3, 4, 5, and so on, 1, 2, 3, 4, 5. And طبعا this is symmetrical matrix. We have zeros here and the diagonal entries. And of course, these are. So you can see the solution number 1, either you go vertical or horizontal, doesn't matter. So you go, this is solution 1, and you compare with all the distances here. And you go for solution 2, and you compare all distances here. All are zeros except the one in the neighborhood. You circle, you have the distance here, you have sigma shares defined, then you calculate, and so on. This is why I mentioned the minimum value of M is at least 1 of all the solutions outside the neighborhood. The sharing here of this solution is 1. I hope this would be clear now.
Dr.
Yes.
Maybe just a quick sigma share, is it one value here?
Yes.
Predefined?
Yes, predefined value. This is
So,
predefined value.
And this is range from what to?
Actually, as we mentioned, if you measure the distance between the extreme points and you divide it by 10. So this is the neighborhood. Sigma share equal to 10% of D max. Okay? Is it clear? So this is fixed value, and you define it at the beginning, the sigma share. And you measure the distance among the solutions. Okay?
Yes.
and you see the distances here, which one of those will be less than sigma share defined?
Yeah.
If it is less than sigma share, you calculate it. Otherwise, it becomes 0.
Okay.
And then you add them up.
Okay.
This is for the solution number 1. You have M1 here equal to 1.5, 2.25, for example. Okay, or 2.6. So this is the M1. You repeat this for solution number 2. You have all the distances. You identify which one is less than sigma share. You calculate it. So D21, D22, D23, and so on. And then you can get the sharing here. Is it clear, Fawzan?
Yes, but Doctor, sigma will it be in, let's say, in order, when we said the range of sigma share here, should it be greater than 1 or less than 1?
Definitely less than 1. لأنه بص look
Yeah.
Fawzan. If we normalize, this solution will be 1, 0 or 0, 1.
Yeah. Yeah.
لا 1, 0. خليها 1, 0. Okay, and this solution will be 0, 1. This is the minimum for F1, so it will be 0. And the maximum for F2, this will be 1. And this will be 1, 0. Am I right?
Yes.
So the distance is 1 square plus 1 square. So 1.4. So this is the whole distance. This is the whole distance. If you divide this by 10, so it becomes 0.14. This is sigma share. Okay?
Yes.
That you can set. You can set, of course, you divide by 10, you divide by 20, you divide by 5. Whatever yani, you can. This is a subjective, as we mentioned earlier. Is it clear?
Yeah, but that's mean, Doctor, the M usually will be a negative value.
Negative? Which one?
And what I'm trying to say now, if we go with 0.14, and the whole term will be higher, 1 minus big term here.
No. Now Dij.
Yeah.
This is the maximum distance. This is the maximum distance. Okay?
Yes, but we are dividing by 0.14 and we square it as well.
لا ما هو خلي بالك. If Dij is greater than sigma share, we are not calculating from here. It is 0.
Yes.
We will not calculate from here unless Dij is less than sigma share. So this will be fraction less than 1.
Yeah, now clear. Yeah.
So if the solution is outside the neighborhood, so the sharing here value equal to 0. Is it clear?
Yes.
Nasser, do you have a question, Nasser?
Yes, doctor.
Yes.
First, the time is over, but also I have a question.
Okay, go ahead.
If there is any values or representation for M, if it is coming, for example, for the solution 1 with respect to the other distance as the summation is coming 2 point, and then when I do for the solution 2 with respect to other, the distance is coming 4, does it mean this is in a crowded area or not? No, but I'm looking.
Okay, if the solution, if we come here for M3 مثلا, and we found it 1, that means this solution is single, nothing in neighborhood. If it is 4, This is more crowded than this one.
Yeah, but the question is, I'm including. Yes, also because we are excluding the one out of the neighborhood by 0, so I'm only talking about the one is around me. That is okay. Now I get it.
So
Yeah,
this is more crowded than this one, and of course this is less crowded when sharing here is 1. معناه there is no single solution in the neighborhood. Okay?
And whatever is below the sigma, I can also just put it in my cluster in this area.
Yeah.
Okay, clear. Thank you, Doctor.
Okay, so this is the sharing. You sum all the sharing with respect to the solution number 1. So degrade the dummy fitness FK. FK is given earlier. FK equal to 10 مثلا. FK equal to 10. Now we will divide by the M. We will divide F by M. So the minimum value of M equal to 1. So it will be kept the same. But if M equal to 2, then we divide FK over 2 for that solution. If it is 4, if it is 2, 3, 1, and so on. So you can have now a modified dummy fitness that reflects the crowdness. Is it clear? We start with M, with 10, and we have different solutions here. Assume that the M share for this one will be 1. Seems nothing in around. Also, M here is 1. The M here we have here 2 solutions, so we will degrade each other. So this becomes 1.5, and this one becomes 1.2. So you divide 10 for this solution, 10 over 1. For this solution, 10 over 1. For this solution, for these solutions, 10 over 1.5. For this solution, 10 over 1.2. So when you select any 2 solutions here and you want to compare, you compare based on F star, F modified. So definitely if this one and this one is selected, definitely you would select this one لأنه الفتنس بتاعته is higher than this one. This is the idea. Any question? Any question? This is the fitness sharing. This procedure is continued, of course, for for all the fronts, for all the fronts. The smallest value will be taken. Here for this example, the minimum value will be over this one. This is the minimum in this front. This fitness will be the minimum. 10 over 1.5 and 10 over 15 and 6 point something 6.67. Okay. So this is the dummy fitness for this front. This is the minimum value of this front. So the next front, we will start with the lower than this. We assume that in the next front, we will take the dummy fitness equal to 6, which is lower than this. And then we repeat the sharing and we divide 6 over whatever the value of the sharing. And we select the minimum value and we subtract epsilon and we start with this next front and so on. So this is the idea here. We identify the minimum. For the first front, we subtract epsilon, and then we get the the raw fitness. Let us say raw fitness for the second front, and then we do sharing, and we modify this value by dividing on the sharing, and we identify the minimum, we subtract, and then we have the dummy or the raw fitness, and we modify it according to the sharing and so on. Do you have any question? Hisham?
Yes, Doctor. I would like to ask about this fitness sharing. May some solution, for example, the ranking one or the best ranking will be moved to other rank. Am I right?
No. Why?
Because
Why?
now we are decreasing the
This
the
is what we
fitness.
do here. And here, we decrease the fitness, you are right. But now we do it sequentially, by the way. And maybe at the beginning, and I just want to say, you know, maybe this is the first front, مثلا. Okay. And this is the second front. This is the third front, and so on. What you'll do, you identify you do the fronts, of course, or ranking. Is it clear? You do ranking. So this is the first front. And this is the second front. And this is the third front. Okay? طيب, now let us start, you know, set the fitness. I will start with this one, الفتنس, raw fitness, and then all raw fitness, 100. Raw fitness for all these solutions, 100. Okay? And then I will go to the sharing here. Definitely these solutions are very near to each other. These solutions are very near to each other. Now, طبعا you have to calculate the distance and so on. And you set the sharing, sigma share, and you see the distances. These ones are lower than, the distance here is lower than sigma share. The distance here is lower than sigma share, and so on. So assume that, you know, the solutions here, sigma share here is 1, sigma share is 1. Sorry, not sigma share. Sharing of this solution is 1. Sharing of this solution is 1. Sharing here is 1.2. Sharing here is 1. There is nothing in near. And sharing here is 1.3. So what you will do, you will divide this raw fitness over the sharing. So this will become 100. This also will become 100. This will become lower than 100. This will become 100, and this will become lower than 100. Okay? You identify the minimum. What is the minimum fitness here? For those solutions, this will be the minimum, which is 100 over 1.3. So this would be, 13,
75.
Yeah, 75. Okay. 75. So this is the minimum in this rank, 75. So I will start the raw fitness for the second front lower than 75. So I will start with 70. Okay? I will start with 70. All these solutions will have a raw fitness equal to 70. And then I will do the sharing here also. This one is 1, nothing in the neighborhood. This one is 1, this one is 1, this one is 1.2. You will divide 70 over this, 70 over 1.2. So the minimum is here, like, for example, 70 over 12, so 6. So this will be like 60. The minimum is 60. So I will start the raw fitness here to by 55 or 50. Whatever, you just, this is a dummy fitness. مش لازم يكون epsilon is constant and all. Just reduce it by a certain value. So this is the raw fitness, and you can do the sharing and so on. So this will be repeated. Okay. So when you select any two solutions for mating and you want to select the parent, you will look at the dummy fitness here, which is 100, 180, and 75, 75. You compare this 75 with whatever here. This one will be, 50 over maybe 50, and you compare it. You select the best one. Okay, Hasham?
Yeah, it's clear. The second question about the segment sharing, the value will be the same for all ranking, for
Yes.
all front.
For all.
It will be constant.
Yeah, it will be constant. خلي بالك is defined in normalized values. يعني when you measure the distance, you have to normalize the objectives. You cannot use the actual objectives. Did you get the point?
Yeah, I got it.
Okay. Any other question? Any other question? Again, بعد ما ناصر قال لنا التايم is over, we spend 15 minutes more. Sorry for this. طيب, okay. If you don't have any question, so you can leave. If you have a question, stay.
Doctor,
Yes.
just about the arrangement of the so now it's only have, I think, 2-3 weeks, something like that, or not less than a month. So before, I think we have 2 months till the final exam. So what will be the new outlines?
Well, so far, as I mentioned, we are waiting for any instruction from the university. What should we do when the final exams will start? What should we do with the remaining material? Should we reduce it? Should we skip some parts? What should we do? If we have, for example, 2 weeks for the exams, that means we may have